So, in this lecture, we're going to talk about the localization of Dedekind domains, and I'll give you a couple sentences of motivation for what we're about to start working on. So, our first goal in this section of Milne is to prove that that ideals, basically, is to prove the following. Let A be a Dedekind domain then every ideal, I guess maybe I should say non-zero ideal. Well, even the zero ideal, I guess I should. Every ideal. I probably need non-zero. Sorry. Every non-zero ideal. A factors uniquely as a product of prime ideals. As A equals P1 to the E1 Pn to the En for some prime ideals Pi and integers EI greater than or equal to 0. Okay. So this is the first major theorem we're going to prove. Basically, and it's a result that's super foundational for the rest of algebraic number theory. I should remark, so why am I factoring ideals as opposed to just elements of the Dedekind domain? Well, it turns out that that Dedekind domains can fail to be UFDs. So in particular, the simplest example is z joined root negative 5. You can check. You probably have checked, maybe in your field theory class, that this ring is not a UFD, and it turns out that this is the ring of integers and Q adjoined root negative 5. So this is not a UFD, but we can recover some semblance of this unique factorization. Unique factorization of ideals gives some recovery of being a UFD, I guess, maybe. So not every Dedekind domain is a UFD, but they all satisfy this thing where the ideals factor as a product of ideals. And yeah, so we're going to spend probably the next 2 or 3 lectures proving this and working through what it means. Today, our main goal is to just talk about the localization of Dedekind domains, prove a couple lemmas here that are going to allow us to then prove this theorem about unique factorization. So today, the overview is going to look something like So we're going to do two main things. We're going to prove some lemmas on localizations of integral domains. And then we're going to look at what happens when I localize a Dedekind domain. So we're going to prove the following. A Noetherian integral domain is a Dedekind domain if and only if each localization at every prime ideal is a Dedekind domain. So essentially what this second condition says is if I've got an integral domain which I already know is Noetherian, to check it's a Dedekind domain, I just have to check locally. I just have to check at every prime ideal. Okay, so just to remind you what a Dedekind domain is, recall an integral domain A is a Dedekind domain if three conditions hold. A is integrally closed, two, every non-zero prime ideal of A is maximal, and three, A is Noetherian. Okay. So these are the three important conditions for an integral domain to be a Dedekind domain. And we're basically going to investigate how these things change under looking at localizations. So this is going to be 26.1 proposition. We're going to let A be an integral domain and the claim is basically to check that something is integrally closed, it suffices to check locally. So then A is integrally closed if and only if A localized at P is integrally closed for each prime ideal P. Okay. So I prove this. So first we're going to show that if A is integrally closed, then each localization is as well. So let's go ahead and let alpha be in the fraction field of A, and let's suppose alpha is a root of monic, let's say f of x in AP. So we're just going to do this from scratch, basically. If, let's say, f is given by this, ci over si, x to the I, this should be from 0 to maybe, well, yeah, this will be fine. And then you just assume that the leading coefficient is 1 with, so all these si's. So these ci over si's are elements of A localized to P. This just means that these si's are not in P. Okay. And yeah, like I was saying, Cn equals Sn equals 1. So if f has this, we see that for s equals s1, so basically the multiple of all these denominators, for s equals this guy, 0 is s to the n times f of alpha. Since f of alpha is 0, this is just 0 too. And then this is I equals 0 to n ci over si times s to the n minus I s alpha to the I. Okay. So what do we see? Basically, from this I can cook up a monic polynomial in A with s alpha as a root. If g of x is this thing, I equals 0 to n ci over si times s to the n minus I xi. Well, we see that again this is going to be a monic polynomial. G of x has coefficients in A, since the s basically cancel out with all the si's by our choice of s as like the product of all these denominators. And we also see that g of x is monic, has lead coefficient s to the n minus n, which is going to be just 1, so s to the 0 is just 1, and Cn over Sn, we saw this was just 1 as well. I guess we not so much saw, we just defined it that way. Thus, what do we see? This has, okay, what do I want to say? G of x is monic, g of x lives in A of x, and g of s alpha equals 0. Hence, s alpha is in A, and alpha, which equals s alpha over s, is in A, localized to P. Since each, since each si is not in P, as s is not in P. Since each si is not in P and P is a prime ideal, s is also not in P. Okay, so there's one direction of our 26.1. Let's go ahead and think about the other direction. Now suppose each localization localization A sub p is integrally closed. Okay. So now we're going to show that alpha, given alpha, so let's say let alpha and frac A be integral over A. Well, then necessarily it's integral over each A sub p. Since, well, A is contained in AP. Thus, alpha is contained in AP for each. So by I should say for each prime P, by hypothesis. So since each A sub P is integrally closed, alpha has to live in each AP. What does this mean? This means, so for each prime P, we can find a denominator S sub P. On P such that S sub P times alpha is an A. So this is just what it means for alpha to be in each AP. This is just like a direct translation. We're going to consider the ideals generated by these S sub P's. Okay. And the thing to note is that this ideal here is not contained in any maximal ideal. Note that this ideal cannot be contained in any maximal ideal. Because, let's say M, since by definition, basically, S sub M is not in M. And here I'm using the fact that every maximal ideal is necessarily one of these prime ideals as well. Maximal implies prime. Okay. Thus, what can I say? This has to be the unit ideal. So here I'm using the fact that every proper ideal is contained in a maximal. You take the contrapositive. If I'm not contained in any maximal, then I must actually have the unit ideal. Okay. What does this tell me? This tells me I can find some CIs. We can find a collection of CIs in A and a collection of PIs such that sum from I equals 0 to n CIS PI equals 1. So since this is the unit ideal, it must necessarily contain 1. So I can find some finite A linear combination of these S sub P's that gives me 1. And then alpha is going to be alpha times 1. I can replace 1 by this sum. CIS PI. which equals sum I equals 1 to n ci s sub pi alpha. Each of these is an a by the definition of s sub pi. Each of these coefficients is an a, so this whole thing is an a. Thus, alpha is an a, and that's exactly what we were trying to show. So since we started with something integral over a, it lived in each localization. And the intersection of all of these localizations actually is the ring A itself. Okay. So this is the general useful fact about integral domains. An integral domain is integrally closed if and only if each localization is integrally closed for each prime ideal. So the next thing I'm going to prove is this second condition, or second statement on Dedekind domains. This is 26.2 proposition. We're going to let A be an integral domain, a Noetherian integral domain. And let's say together, A is an Noetherian integral domain. Oh, sorry, yeah, this is mostly just a short lemma. And then we'll actually get into the proposition I stated earlier. Then I just want to say each localization is Noetherian. And to prove this, you basically just need to use one fact. Proof. Use the descending chain condition. Together with the inclusion preserving bijection between ideals of A contained in P and ideals of A localized at P. Okay. So this guy here is one of the fundamental facts about localizations. If you use the descending chain condition together with this fact, then the fact that each localization is Noetherian follows pretty quickly. Okay, so now I can actually state and prove the result that I was thinking about. Okay. 26.3 proposition. So a Noetherian integral domain is a Dedekind domain if and only if each localization is a Dedekind domain. And so we've kind of done a large bulk of the work. Proof. So first let's suppose A is a Dedekind domain. Now we need to show each localization is a Dedekind domain. let P subset of A be prime. Well, by our two lemmas, I guess I should say by 26.1 and 26.2, well, A is a unique factorization domain, or not A is integrally closed and Noetherian. So by 26.1 and 26.2, A localized at P is integrally closed and Noetherian. Now it just remains to show that every prime ideal in A is maximal. So I'm going to let Q subset of A localized to P be prime. Well, then Q corresponds to some prime ideal contained in P. Oh, I should say be a non-zero prime. Then Q corresponds to A prime. Q tilde, subset of P, subset of A. Okay, and well, P is maximal, or what do I want to say? Since A is Dedekind domain, Q tilde is maximal. And hence Q tilde equals P, and this forces Q to equal PAP. Okay, so this PAP is the only prime ideal in A localized to P. So we see that A localized to P is a Dedekind domain. Okay. So now we need to kind of go in the reverse direction. This is slightly more work, but not too bad. Let's suppose each localization is a Dedekind domain. So by hypothesis, A is Noetherian, so that condition we don't have to worry about. And by 26.1, A is integrally closed. So each localization is integrally closed, so we know that A is necessarily integrally closed as well. Then basically you run this argument in reverse. So the fact that every prime is maximal follows from the correspondence theorem. And the assumption that each A sub P is maximal. Or not PA sub P is maximal, that this is the only ideal in A localized to P. So basically, if like P1 were contained in P2, then I could look at A sub P2, and then P1 would be a prime ideal in A sub P2, or would generate a prime ideal, which would force that P1 and P2 are the same in the localization by the Dedekind hypothesis, and then by the correspondence theorem, this would force P1 and P2 to actually be the same in A. Okay, so that's pretty much all I want to say. So the moral of this lecture is that we proved that being a Dedekind domain is a local condition. And this is going to turn out to be useful. So in the next lecture, we're going to talk about a little bit more about what it means to be a local Dedekind domain. Turns out that these local Dedekind domains have a lot of structure to them. And we're going to talk about basically what class of rings these local Dedekind domains fall into.